review our next speaker for the second seminar of the Department of Applied Physical Chemistry and Postgraduate School for the University. Professor Ferry Prins is a professor permanente laboral of this university. He has a very extensive history. I will give you some small details of him. Since spring 2017, he's a member of the Condensed Matter Physics Center, IFIMAC, at the Autónoma University of Madrid, where he directs the photonic nanomaterials and devices lab. Ferry has been recipient of a number of awards, including the Rubicon Award in 2011, the Ambizione Grant in 2015, la Comunidad de Madrid Talent Grant in 2017, Harmonic Sound in 2015, and he's now recipient of the ERC Consolidator Grant in 2023. Has been teaching experimental techniques in the second year of the physics, the bachelor, but he is always coordinating the university-wide course on climate change since 2023. Ferry, welcome to this series of seminars. Thank you very much.
Fine. Thank you very much. So I'm very happy to be here. So the Doctoral School of Physical Chemistry, even though I am part of the Condensed Matter Physics Department, Module 3. I'm a trained physical chemist a long time ago, so I'm happy to be here as well. What I would like to present today is a series of experiments that we've been developing over the past, I would say, 10-ish years that focus on the question of how excited states, whether or not they're excitons or free charges or heat, or how they move through semiconductor materials. And the idea that we have there is to try and make movies of these carriers, how they move through the material with few nanometer and sub-nanosecond resolution. I'm going to explain a little bit what are the tricks that we use to get there. We are doing this mostly on nanostructured semiconductors because that's where these questions are interesting. If you take a perfect piece of silicon, the transport properties are quite boring because it's a perfect crystal and things are diffusing and everybody understands that. It's not very new. But the real question comes that once your semiconductor is nanostructured, we're going to go into why we want them to be nanostructured. If they're nanostructured, then the transport becomes way more complex because it's going to be disordered, it's going to be not so perfect. And the question that we want to answer is, okay, so what happens when it's not so perfect? Why do some of these materials actually work really well, even though if we look at the morphology, they're quite bad? And what can we then learn to try and improve these materials even further? Okay, so if this works, most important slide first. I did do very little of the work that I'm presenting. The work has been done by a group of very talented PhD students and postdocs. This is the group right now. We are approximately 10-ish, where we have about 5 postdocs, 5 PhD students, and then a group of interchanging trabajo finalado, trabajo final master, Erasmus visiting students. And I would also like to highlight the work of Natalia Leon, which is the project manager, without whom I would be very lost, most of the work that I'm doing. And then, of course, we have a lot of alumni which have passed through the group over the past 10 years. And of course, we cannot do any of this work either without the funding agencies that support it. Okay, so I'm gonna highlight the work of many of these people. Many of the things require both chemistry and spectroscopy and theory. So there's many group efforts in the work that I'll be presenting, and I'll go over that. Okay, so first question first. Why are we so interested, so excited about nanomaterials? I'm just going to give an example here. So the last 10 years, 15 years, people have gotten very excited about perovskites. And the basic reason why perovskites are so interesting is because they are so easy to make. So I'm going to show you a movie here. This is just, for us, an anti-solvent, toluene. And we're just going to inject the precursors and see what happens. So there's room temperature, ambient. All the precursors. The moment that you inject it in the anti-solvent, it crystallizes. Crystallizes into tiny little nanoparticles. These nanoparticles are bright. See the fluorescence. And they are actually quite good, even though you're not trying any effort to make them, high quantum yields or anything. Some of these materials that we are doing at ambient reach quantum yields of 90%, which me coming from nanoparticles in the past of cadmium selenide, you needed to do an incredible amount of effort to actually get those kind of numbers. For perovskites, apparently it just happens. So perovskites are this magical material in many ways that are giving us really good properties without any effort. And then actually when you make a solar cell out of them, they also work almost as good as silicon. And nobody, of course, there's more clues onto why they are working so well, but there's a big question out there still. Okay, can we understand the fundamental physics of the excited state population inside these materials to justify how good they really are? This is a little bit the general motivation for us to say that, okay, if we're going to be working with nanomaterials, we really need to understand what is going on there to be able to explain why things apparently work so well. Okay, so a little bit of a step back now. If we talk about, yes, okay, so what I mentioned, silicon is very boring. You can make it into very nice wafers. You heat it up to 900, 1,000 degrees, and you get a perfect crystal. Characteristics. Well, you have a large epsilon, so dielectric constant. You have weak localization of your excited state, which means that your charges dissociate instantaneously, which results into a very small exciton binding energy. So the exciton that you create is basically just free charges. In physical chemistry terms, we would call this a 1-year mod exciton. Only at low temperatures you will see the exciton, but otherwise you have free charges. Okay, on the other extreme, this is pretty slow. Here. On the other extreme, we have molecules, which if you're a physicist, you would call a semiconductor. If you're a chemist, it's a molecule. And at the end of the day, it is just two extremes of the same spectrum, where now we have a small epsilon. So the excitation is going to be very localized. It's a molecule. It's going to be localized on the molecule in most cases, which leaves us with a very large exciton binding energy. If we photoexcite this molecule, you're going to create what we would refer to as an exciton. The electron and hole are bound, and they will be moving through the material together. So now we don't have free charges anymore. We have an excited state that is an exciton, which is a package of energy which can move around. Okay, this what we call a Frankel exciton. When we go to nanoscale semiconductors, it's a little bit weird because we are dealing with these kind of materials. So we have a large epsilon, because it's still the same material. We just make it smaller. But now because we make it smaller through quantum confinement, which I'll get to in a second, we're actually getting large exciton binding energies. So we have now packages of energy, which are typically excitons, but they are living in this environment, which is this large epsilon. It's a little bit weird. So there's going to be different physics going on here. So in many cases, of course, the interesting stuff happens when we are in the intermediate regime. Can we understand what is going on there? Okay, so quantum confinement. Just to recap, right? This is your typical picture where if you have a very large piece of semiconductor, you have your conductance band, you have your valence band, so bleeding into each other, all these levels, and your excitation is there and it can dissociate. You make it smaller up to some critical point, which we call the Bohr radius. Once you reach the Bohr radius, your excitation would like to be extended, but it cannot because your particle is too small. So now you're creating a particle in a box. It's basically the textbook example. Where we go to smaller and smaller, we see two things. We see discretization of your energy levels, which at the end are just your molecular orbitals that are generating. and you're seeing that the band gap gets larger. Okay, so we're talking about physical chemistry. This is the physicist picture. So you have spatial confinement of an electron hole pair. There's a very nice review by Rumbles and Scholes from 2006 that really goes over all the details. At the end of the day, we are doing nothing else than what we are doing when we go from a pentacene to a benzene, where we are just creating, a larger and larger HOMO-LUMO gap. It's exactly the same physics. There's no magic. But of course, well, here we go in discrete steps. Here you can tune the size of these particles with much higher precision. So you can change the band gap. And this is interesting because this allows us to change the color. Okay, so here, this is an example of this effect, right? One of the textbook examples. This is lead sulfide. So we go from a relatively large particle of 8 nanometers. We have an emission wavelength in the near infrared, 1800 nanometers. And as we are going from 8 to 7 to 6 to 5 to 4, we are shifting our emission wavelength from 1800 nanometers to 900 nanometers. It's just the absorption spectrum, basically just your band gap changing as a function of the size of the particle that you're synthesizing. So now if you can control the size of the particle in the synthesis, you can control the band gap and the color of your material. This for applications is very interesting. If you have a light emitting application, then of course, in the case of cadmium selenide, you are invisible. You start off with red in the bulk and you go to the blue. Then of course, you can choose your LED color or your TV screen color simply by shifting the size of the particle. So within the same chemistry, if you can control the size. And that sulfide, you can control, for example, the absorption of your solar cell, matching it exactly to the spectrum of the sun. While in conventional semiconductors, there's only so few types of semiconductors that we have that already have their band gap fixed. We're very lucky, by the way, that silicon is the most abundant material that we have, and it happens to fall exactly at the peak of the solar spectrum. It's one of those coincidences of nature that we couldn't have predicted better, but here you have the flexibility to actually tune the band gap. Okay, so you can tune the absorption and the emission through the size, but also through shape and through composition. Just very briefly, right now I'm talking about nanoparticles, which would be zero-dimensional systems, which are quantum dots. You can also do the confinement in one dimension, so you let in 2 dimensions. You let 1 dimension extend, you get a quantum wire. Quantum well, basically only confinement in 1 dimension, but the other 2 you're letting it go, and then you have the 3D bulk, which is your conventional semiconductor. And today, in the later results, I'm going to be talking both about 0D and 2D. The physics is the same. Once you start going below the Bohr radius, you start to shift the energy levels and discretize the energy levels that you have. So if you're a good chemist, you can do this. Materials, you can make wires. This is platelets, wires, or particles. Okay. So, if your band gap depends on the size of your particle and you synthesize, then you need to control your size, because otherwise you're going to get many band gaps. So, size polydispersity, if you have a very monodisperse ensemble, you've synthesized your nanoparticles and all of them have the same size, then you're going to get, a very nicely well-defined absorption spectrum and a very nicely defined emission spectrum. If you don't control it so well, then you're going to get a smeared out absorption spectrum, because the smaller particles of your ensemble are going to have a bigger band gap and the bigger particles are going to have a smaller band gap. So polydispersity at the end will result in, your spectral features being less defined. And this is a very important question, because when I showed before that it was very easy to synthesize perovskites, we're not controlling any size there. And actually, that is a very difficult question. It's even a question that is so important that if you solve it, you get a Nobel Prize. So this is 2023, Nobel Prize in Chemistry, where Lou Bruce and Alexei Akimov were the pioneers in the 80s, demonstrating that if you make particles small enough, you get a quantum size effect. But the real breakthrough came when in the early 90s, Moonji Bawendi managed to actually control the size to such an extent that particles became indistinguishable. Even though you have some small variation of your particle size, they all have the same bandgap. And once you can do that, you can advance to really the advantages of the particles. Now, this is for a doctoral school, so I think it's important, you know, to also kind of recap these kind of stories. So, of course, Munji was the PI. He was a very young PI. He started in '92 at MIT as a tenure track. And in '93, they published the paper that, you know, gave the key to size control. And so, even though you don't get to stand on the podium, you still get to go to the dinner if you actually did the work. So this is Chris Murray and David Norris. David sent me this picture. So here, you know, you have the two people. Chris was the synthetic chemist. David was the physical chemist, who basically, you know, developed all the technique and all the interpretation. And I don't want to take away any of the credit from Munji, because Munji is, I think, in my opinion, one of the most modest people in chemistry. But I think it's also important to stress, you know, the work that's normally actually done by the students. So they published a paper. It's really slow. I'm just going to do it like this. All right. They published a paper in 1993, cited some 10,000 times now, which is the synthesis and characterization of nearly monodisperse. I like how back in the days people were still modest even in the titles of their papers. Cadmium selenide, sulfide selenide telluride, semiconductor nanocrystallites. With Chris, David, and Munji as the authors. The key here was what they call now, what we refer now to as hot injection synthesis. I'm just going to go over that in a few slides to explain this. The easiest to explain it is by showing a movie. This is not sped up. This is real time. It's gonna go in a. There's a movie from the Ferry lab, but basically you have a very hot precursor solution that you just take out of your heating mantle, and very fast you inject precursors, and you get immediately your red color. That is your quantum dot. This is the red from the cadmium selenide quantum dot. Why do they do it so fast? You need to do it very fast, because if you do it slow, then some of the material will already start growing, while the others are still being injected, and you get size photodispersity. Because you're working at very high temperature here, where everything happens instantaneously. So timing is crucial here. This is a small-scale synthesis of some 200 milliliters. I'll show you in a bit how I cannot show you how they do it because it's proprietary, but now companies are doing this synthesis on a scale of 5 liters, where you still need to have the same speed of injection. So they basically built guns to inject the solution, your precursor solution, fast enough that everything homogenizes fast enough that on a scale of 5 liters, you can do the same kind of control over size. Okay, that's for a separate thing. The key here is that you are basically, you know, controlling the concentration of monomers. The moment that you inject, you need to get very, very fast above the nucleation threshold. Once you nucleate, there's going to be growth from the precursors that have not yet nucleated. So you nucleate, you start growing immediately. That, of course, decreases the concentration of monomers. So in a one-pot synthesis, you are controlling both the kinetics and the thermodynamics of the system, the growth of your quantum dots. Okay, then you reach a point, it's more technical, and I don't want to go into that because I'm not a synthetic chemist. You have a process that is oswald ripening, where actually they call it size focusing as well. So smaller particles, they dissolve again, but bigger particles, they're already stable. So there's a process that is smaller particles dissolving that then are growing again on the bigger ones, which focuses at the end size until you reach saturation. Like this, you can control the size. And if you can control the size, then you can do physical chemistry. Because now you have a system where you have a perfect set of nanocrystals, where you can now start distinguishing all these different orbitals that we have created, because at the end they're just molecular orbitals. So this is a paper by David in 96, where it's measurement and assignment of the size-dependent optical spectrum of cadmium selenide quantum dots. And this is really beautiful. here, you know, you have a photoluminescence excitation spectrum that you can then, you don't even see the fit because it's right there, but you can basically extract all the different orbitals of your particle in a box, of your molecule. And you can follow these by the decreasing radius and everything. Right, this has evolved through many, many years of more and more development. Now it's not just carbon selenide, there's many systems that you can do in different regions of the spectrum. And it's just a really nice textbook example of what you can do with inorganic chemistry. You manage to control the kinetics. It's the key. So if you're interested, so David is coming to visit. I owe a lot of my career to David. I worked with him for 2 years. He is one of the nicest people as well in chemistry. So he's coming on January 16th to visit here for an IFIMAC colloquium in module 0. Okay. So now we can make nanoparticles, we can grow shells on them, they can be very, very advanced. And then now you go to your media market and you can buy a TV that has the QLED label. That means that at least the red and the green are these kind of quantum dots. Whether or not they're cadmium selenide or indium phosphide or the red and the green in those cases are these quantum dots, because at the end of the day, if you can make a very nice sharp emitter, you get higher purity of your colors in your TV screen. And this is the key. If you have organic fluorophores, actually their emission spectrum is quite large normally, quite broad. So the green is not just green, but there's also a bit of orange in there. Quantum dots have the advantage that when you make red, you make red. Okay, good. So this was my introduction a little bit to why we are interested in nanomaterials. Why are we interested in making semiconductors, you know, nanostructured, controlling size and shape. So you can do all this. You can change the composition, you can change the size, and you can get all these colors. And then you can make thin films. But of course, here you have a perfect building block that is in solution, that is isolated. You can study the physics of that. But then you put it in a film, and then everything is suddenly connected. So your excited state is going to want to walk around, or maybe not. But the question is, what happens to that excited state when you suddenly put all these particles in communication with each other? And what happens then? Because now you don't have a perfect semiconductor, you actually have the most imperfect semiconductor, because you have the most polycrystalline film that you can imagine. It's all tiny crystals separated by organic ligands that are at the surface. So you have grain boundaries everywhere. So now what happens? That's a little bit the question that we like to answer in our group. So in our group, we have 2 parts, and I really don't have time to talk about both. We want to basically understand and control these kind of excited states to understand better and control better the kind of physics that we can explore. So this is a lot of photonics. I cannot talk about that today because I don't have time, but I'm going to be talking a lot about how we try to use our microscopes and our spectrographs to understand better what is going on in these materials. Good. Good. So if we can make semiconductors at low temperatures, not at 900 degrees of silicon, then we can start thinking about making semiconductors on polymer films and have more flexible devices. Good. So that's a little bit the motivation. But if you do it at low temperature, then you have all these morphological problems. You have the morphology of your film, which is basically how is your nanoparticles or your nanostructured material packed. You have maybe, if you don't control your polydispersity well, then you're going to have side-to-side energy differences in your film. All the grain boundaries that you have, which are intrinsic in a nanocrystal film, are going to have traps, are going to be impeding maybe how a carrier moves through the material. So there's all this disorder that is going to affect whatever we're trying to resolve. Okay, so if we want to learn something about that nanostructured morphology, we're going to have to be looking at the nanoscale. But if we then use an optical microscope, we run into a very fundamental law that is just fraction limit, which tells us that my beam waste, no matter how expensive my objective is going to be at best at around 250 nanometers if I work in the visible regime. So we're not going to be able to resolve anything below that 250 nanometers, basically your standard heavy diffraction limit, where you have two fluorophores, you cannot distinguish one from the other if they are situated below that diffraction limit. And so 250 nanometers more or less is our hand wavy limit that we have. But our structure, if we have nanoparticles, is below that. So if we want to learn something about nanoscale transport, we need to play tricks. And the trick that we are using, and there's a lot of different types of super resolution microscopes. This is one of them. Here I put breaking the diffraction limit, which is misleading because we're not breaking anything. We're just playing tricks. Nobody breaks, this is important. Everybody that says super resolution imaging, we're breaking the diffraction limit, nobody breaks the diffraction limit. You can get around it, but you cannot break it, right? This is important. So this I put here kind of deliberately. We never break the diffraction limit. So what we can do is tricks. So I talked to you about the point spread function, right? So the point spread function is my 250 nanometers. That is the highest resolution that I can do. So what I can do is I can create with a laser a population of carriers that is at the diffraction limit, 250 nanometers. I cannot measure below that. And I cannot generate a population that is smaller than that with my normal optics. What I can do, though, is that when that population starts moving in time, that population becomes broader because they're diffusing outwards, I can measure the point spread function at a different point in time. And that point spread function is going to be bigger than the original. And I can measure the difference. And I can measure the difference between the population at time is 0 and the population at time is x with a resolution that is below the diffraction limit. Because I'm never breaking the diffraction limit. What I'm doing is measuring changes in the point spread function smaller than the point spread function itself. But I'm never breaking the diffraction. I'm just measuring a difference here that happens to be very small. But neither one of them is below the diffraction limit. And that is the trick that we play to at the end be able to say like, okay, so now once we've created this original population, its movement, we can measure it with a resolution better than the diffraction limit. So this is the starting point of what we're trying to do. Okay, good. So this is not from yesterday. This is now, well, time goes by. So now we're 2025, 11, 12 years ago. So we were a very young group of people. With me. This is Will Tisdale, which at that point had just started his tenure track as well. This is a group at Boston at MIT. The average age of these people was about 26. So Will was 29 years old when he started. I was 28 as his first postdoc. And then everybody else was much younger than us. It's a very young team. And we set out to answer this question, right? To try and develop this technique. Well, this crazy idea. Is this possible? So how do we do this in practice? We take a microscope, I mentioned, you take a pulsed laser, excitation laser, you create this diffraction limited spot. And now you collect the fluorescence from the carrier, like you create excitation, and at some point they die, they emit the fluorescence, the fluorophore, fluorescent photon, sorry. You collect that outside of the microscope. Now what you do outside of the microscope is you put a very large magnification. This is like 400 times. You use your lenses, you make 400 times magnification of your population, the emission of your population. And now you take an avalanche photodiode, an APD. An APD, what it does is it can measure lifetime. That's our time axis of our movie. But the APD, compared to the projection, the image is actually very small. So it's like a pixel within this gigantic thing. If you now put the APD on a motorized stage, then you can start taking, lifetime measurements at each point in time. That means that you're having a scanning pixel, which at the end gives you your image, and you have your time axis from your lifetime measurement. So now you can reconstruct little movies of how this population starts moving through the material. Okay. Time, image, and it broadens as a function of time. Now, instead of taking an entire movie, if you have a material that's isotropic, everything moves in the same direction, same speed, then what you can do is you can reduce your acquisition time. You just take a single slice through your population, and you now see, so now you have time is 0, position. So here at time is 0, we have our 250 nanometer north, that's really matter, original population. And then as time goes by, we see the population broadening. What's important here is I've normalized out the decay of the excited state so that we focus purely on the broadening of the population. So now you can see that this population, initial population, is broadening in time, and we can start analyzing that. You can see it clearly if you take time slices. So just compare how broad it looks. Time is 0, very narrow. And then as time goes by, on a nanosecond time scale, you see population broadening and broadening. Okay, this is all qualitative, but you can quantify this. Take the variance of that maximum of your population at this point in time, and we're going to compare population at a point in time t with the original one. Yeah, square it, and then what you get is what we call a mean square displacement, or in this case, actually a mean square expansion of your population. Yeah? How fast does it expand? You can plot that. What you get is, as a function of time, mean square expansion, how fast does your population broaden in time? Now, if I would have normal diffusion, just like random walk diffusion, I would get a straight line here. The Einstein relation. And that straight line, the slope of that would give me my diffusivity, proportional to my diffusivity of my material. Most cases, what we see is, well, we almost never see a straight line. We almost always see something that slows down. The slope gets smaller and smaller. So the slope is fast in the beginning, but slower later on. And this is our first indication of disorder. You excite everything equally, but now your energy landscape has like all these valleys, and your carriers tend to go down in these valleys, and they get trapped in the valleys. And when they get trapped in the valleys, they cannot move as fast as when they are on top of the mountain. We're going to get to that in a second. Okay, so these were very early studies at the original group with Will Tisdale. And by now, I'm very happy to see that many people have adapted this, and more and more people are working on this. And since 2017, we've been also contributing further on this with a series of perovskite papers. So, questions. What can the spatial dynamics, how these carriers move, teach us about the material and about its energy landscape, right? If you slow down fast, probably you're going to have more disorder. So we can learn something from that. Okay, this is an early study, but I think it's very, it's a very good example. So here we have these nanoparticles, right? Cadmium selenide. And what we know is that, well, there's excitons there, and an exciton in a nanoparticle, if it hops to the next one, it's going to be energy transfer. So this is a Förster-like process, right? Förster energy transfer. So what is important is the distance between the dipole that you have here and the dipole that you have there. Yeah? So it's the distance between the center and center of the particles, and we can change the chemistry a bit to control that distance. Yeah? So it's the same kind of particle, but now we are going from 8 to 8.3 to 12.6. And we have this system, and we have a film, and we can study how the transport is different in each one of these films. Yeah? So we can do our measurements. It's very subtle in this case, but you can see that it's broadening as a function of time. For that maximum, it's increasing as a function of time. Then we can quantify this for all three. How fast does my population broaden as a function of time? And then I have my short distance and longer distance. Short distance and longer distance. So you can see that it's clearly slower when I space my particles out further, which makes sense because Förster is very sensitive to the distance between particles. So as I space them out, the dipole-dipole coupling gets weaker, and my particle doesn't hop as efficiently from one particle to the next. That's what we're seeing here. What we're also seeing is that none of these three shows a straight line. They all show that they are slowing down as a function of time, which is an indication of disorder. So we can fit these curves were parallel. We just take a parameter alpha, which tells us how fast is it slowing down. And one step first, yes.
And this is the diffusion and the diffusion of the left one particle to another, or the diffusion of the exciton.
In this case, we're talking about excitons. Because there's no
you know that the exciton and not the left.
So if you want to distinguish between excitons or free charges, what you do is you look at the power dependence fluorescence. If you see that the fluorescence that comes out of your signal is directly proportional to the laser excitation power, you know that they're excitons because it's a unimolecular recombination. Whereas if they're free charges, they need to find each other before they can emit, and then you're going to see something that resembles a quadratic. Okay. The one thing that's important to realize when we have this kind of subdiffusive behavior is that in the beginning we're moving fast and then we're going to slow down. So here you plot basically the first derivative of this fit, where you see that everything starts off fast and it gets slower and slower as time goes by. And this alpha parameter then 0.7. I'm going to get to this in a minute. 0.7 now tells you like, okay, it's slowing down. Fine, it's slowing down. Why is it slowing down? Well, again, these particles were actually not perfect. So there's got to be some size variation. So I'm going to have some particles that are higher in energy, other particles that are going to be lower in energy. I excite all of them more or less with the same probability. As I turn on my communication between the particles, they start moving around. They prefer to move downhill. So when I'm beginning at a blue one, probability is higher to move to lower energy sites than actually the transfer between high energy sites and high energy sites. So as time goes by, if I have movement of particles, they're going to go to the values of the energy density. Once you reach this one, it cannot give up its exciton anymore because everything is energetically uphill. So you can imagine that if you're diffusing in a disordered energy landscape, you are populating more and more lower energy sites, which have less and less possible escape pathways. So at the end of the day, the diffusion slows down. Yeah. Okay, so that picture is very important, especially in quantum dots. But you can, I can tell you this, and this is a hypothesis, but you can measure this, of course, as well. So here, and plotting it quite small, realize this spectrum is a function of time where you see the same thing. There's this redshift spectrum, and that redshift coincides with the slowing down of your transport. Okay. People always see this and then they always the same question, oh yeah, but how far do they actually travel, right? Fine, they move fast, but they also live short. Here is basically just like crunching the numbers. So the average propagation distance of an exciton is, well, basically these 3 points is defined as the diffusion length. And you see that indeed, you are increasing the diffusion length as you are decreasing the distance between the particles. This is an important parameter you advise. Also here, propagation distance, we are just here at tens of nanometers. So this shows you the power of this technique, that we are able to measure, to resolve basically the diffusion of particles, which are diffusing only, some tens of nanometers. That also means that actually in a particle film, in reality, the average number of hops that a particle does before it dies is 3, 4, 5 hops. It's quite small. Okay, good. All right, I'm going to speed up a little bit. I'm talking a lot. I'm going to talk about a separate story. Because there's a thing in these motivations to say like, yes, we want to go to we want to step away from the high temperature synthesis or the high temperature formation of silicon. So we're going to make nanoparticles, but now the way to make good nanoparticles is to go to hot injection synthesis, which again goes to high temperature. So like one of the things of perovskites, when we talk about perovskites now, the people are saying like, yeah, it's really great because you can do it at room temperature. Right, but if you want to make really good ones, you need to go again to high temperature, hot injection synthesis, same as with platinum selenide, and then you can make perfect particles and everything looks really good, right? That kind of defeats the purpose. If you want to do something that is on an industrial level, room temperature and easy, unfortunately what you get is this. Yeah. So the little movie that I showed in the beginning, actually the morphology is quite disordered. There's a lot of size polydispersity. This is what they call the ligand-assisted reprecipitation method. This is what you get. Okay. But still, you get this, and you make LEDs out of it, and people see that you can make LEDs that are close to the theoretical limit of how good they could be. So apparently, it doesn't really matter this is again the same story. Perovskites are this magical material where you really don't need to work very hard to get good results. So why is that? Why do these disordered films perform so well? So this is a question that we've been working with over the past year. Simon Solari, there was a postdoc in the group. And basically here, the synthesis is very simple. We just have at room temperature, even though there's here a flask. We do it under argon just for consistency. And we're going to synthesize these that bromide perovskite phase, nanocrystals, lactic acid, and we have the capping ligands, 3 different types. We have either 8 carbons, 12 carbons, or 16 carbons, right? So we're making the alkyl chain a little bit longer. And the funny thing is that already just doing that, you see big changes. These are the TEM images. This is all over the place. C6, C8, sorry. And as you go to C16, the particles get better. You get more monodisperse. Right? Well, these bright spots that you see in the TEM, that's TEM artifacts because you're blasting the thing with electrons. So don't worry about that. But basically, you're making the particles smaller and they're being more monodisperse just by changing the ligand length. Right? This is the binding of the ligand. You get better results at first sight. So we can do some analysis here. We know these are all excitons, independent of the size. So we do this analysis, straight line with PL. We know they're excitons. So what for us is the important thing is the distance, again, between the particles, the center to center distance, because that's where the dipoles are. Right? It's not so much the distance between 2 particles, that would be for electron transfer, it's the distance between the dipoles. So we can do the size analysis, and you can see that indeed for C8, very broad polydisperse ensemble with relatively large size, whereas C16 gives me a sharper distribution, more monodisperse, smaller size. Okay, so which one would work better? Well, if you ask me, it's energy transfer. I would say again, knowing what we know from the cadmium cyanide story that I just told you, that the one with smaller size should give me better transport. Moreover, it looks better, and also the polydispersity is less. Okay, so let's get into that. Here, linear power dependence, we are dealing with excitons. We can look at spectra, emission spectra in solution. We see that there is a little bit of quantum confinement kicking in for C16. Yeah, the smallest particles have bluer emission than the other 2. That's good, that's normal, that's what we expect. We see the same thing in the film. So there's something funny here. If we really look at the forward at maximum of the emission, then we see that the more monodispersed particles, which are supposed to be better defined, are actually having a broader forward at maximum. It suggests that actually energetically they are less similar. Here we have multiple band gaps. Whereas in the other one, we have a better defined band gap, even though they're much more polydispersed. We can see this also again in these kind of time-resolved spectroscopy measurements. So we take the spectrum as a function of time. In all 3 of them, we see this redshift. So if you make a film, again, the particles are moving downwards in energy, but you see that the redshift is much larger for the C16, even though they are the more monodispersed ensemble. So why, if you make particles that are by eye better, do you have more energetic disorder? This doesn't make much sense. So this is the delta E, that's basically like where this one ends, where your delta E is larger, minus 22, this is the direction, for the more monodispersed particles. What's this picture again? You're having a redshift, and you would have this exciton funneling. That doesn't make much sense if the particle distribution is much better. So what is going on here? If you take these kind of particles, which are small, what we can do is we can plot their diameter as a function of the band gap that we measure. So the diameter has a certain polydispersity, calling that here as the error bar in my diameter. And then I measure the band gap energy or of the different ones that we measure. Now, if you take a very, it's not a fit, it's just like a guide to the eye. You want to fit something to 3 data point, but this is basically what we're seeing, right? Now, what happens is that if I have these very large particles where I'm not yet very quantum confined, then adding an extra atom, or adding a couple of extra atoms, is actually not changing so much my band gap energy. Whereas if I'm more quantum confined, adding even a single atom is already going to change my band gap energy quite dramatically. My slope here, my sizing curve is very different. So this would be an explanation as to why smaller particles, even though they look more monodispersed, at the end are going to result in something that is more energetically disordered. Okay, so now we have two things. On the one hand, I have structural disorder because the morphology of this film is really bad. A lot of like different sizes and they don't pack well. Here I have better packing and better size distribution, so less structural disorder. But my energetic disorder apparently is bigger here than it is there. Okay, so now we have a system in which we can ask ourselves the question, okay, so what is the consequence of this? What happens to the transport? Right? Structural disorder dominant is energetic disorder dominant. Exactly. That's the question I want to ask. So now we go to our transport measurements again. Do again the same measurements. For the C8, you see that it broadens as a function of time. All good. We can quantify all this. Now we get the same kind of plot, but it's inverted. Right now, C8, which are the biggest particles, is the one that diffuses the best, whereas the small particles are diffusing worse. And if I do my same thing, my fit of the alpha, my power law fit of the subdiffusion, we also see that actually this alpha is getting lower, which means that it's slowing down faster for the particles that at first sight look better, but apparently have a lot of energetic disorder. So we're again doing this exciton funneling, and now it turns out that the energetic disorder actually is at the end so much more important than whether or not your film looks nice. So you're a synthetic chemist and you think like, well, I get this and I need to go back to the drawing table because I need to make better particles. In some cases, in the perovskites, apparently you don't care. Maybe you actually should not care. It's more important to make particles that are, you know, energetically similar. So this again is the diffusion length. The nanometers, these 8 carbon atoms go about 80 nanometers, whereas the 16 only go 30 nanometers. So now this is kind of like the joke, right? So you tell this in an editor, a letter to the editor, you say like, yeah, my shorter ligands are giving me better transport. And everybody will be like, sure. It's not very surprising, right? Okay. So of course, the key here is that these are excitons, so you should not care about the ligand length. You should care about the distance between particles. That's important, right? So if I have smaller particles, it should be better. It's not. On top of that, if I make a smaller particle and it's more excitonic, I also should have a larger dipole strength, which again should promote transport. It doesn't. So while the easy conclusion would have been this, you said, yeah, sure. If you actually go into all the detail, you see that things are more complex. And if you want to optimize your system, you should not go to shorter and shorter ligands. You should go to a system that has the most flat energy landscape. Yeah? So it's a different parameter that you need to optimize if you want to optimize transport. Okay. How am I doing? This is 50 minutes. All right. I'm going to go very fast through one thing. I want to show one more thing. So I'm going to, yeah, here. So 2D systems, 2-dimensionals. But this is also perovskite. This is your broke perovskite. And you just do your synthesis without any organic long ligands. You just get an infinite system of corner sharing octahedra. Then you introduce long cations, which act as scissors. And the ratio between these longer cations and your original precursors allows you to control the thickness of your inorganic layers. Now you have a two-dimensional layer that can either contain, for example, 3 octahedra of lead iodide, lead bromide, or 2, or 1. I'm going to focus on this one. Here you have the two-dimensional quantum confinement. So you're now making the particle, it's the layer, you're making the layer thinner and thinner, and you're going to see again this shift in the energy. Okay, perovskites are very interesting because you can change a lot of parameters, which makes it a good playground. And then there's a general question of how does composition affect spatial dynamics of excitons, right? I'm going to change a parameter, all these options that I have, and I want to know what happens to the transport in that film of these excitons. How do they diffuse through the material? So I can synthesize, this is phenethylammonium, it's a nice benzene ring that is separating the ligand, the films. I take a crystal, that's exfoliation, and we can measure. This is what we get. This is a nice measure. So here actually, is phenethylammonium, lead iodide, time versus rho. You can see that it slows down, but if you really look carefully at the beginning, there's actually a regime that now is a straight line, and only at later points you see that it slows down. So apparently in these crystals, excitons move around as if it's a random walk, normal diffusion, until at some point they start slowing down. And that point is going to be critical. I'm going to get to that in a second. This is phenethylammonium. And then there was people like, many people were doing this. Either they use phenethylammonium or they use butylammonium or whatever is their favorite organic cation, and they were making devices out of that. So you have phenethylammonium, then you can make butylammonium. These were the two most popular, still are, for many things. Butylammonium is just like your aliphatic chain. Here you have pi-pi interactions, hydrogen pi interactions. Here it's just your aliphatic chains that are hanging there. You do your measurement, and you see this. These are the diffusion maps. Whereas this one, your excitons move very, very easily and very fast. In butylammonium, for some reason, the things don't move. But because we have a super resolution technique, you can still analyze this and still get the same behavior, just at a very different order of magnitude. You still see that it broadens linear still in the beginning and it slows down again. But you get an order of magnitude difference in diffusivity just by changing the organic cation that is separating these inorganic layers, which is where your excitons live. So the organic things should not actually affect very much your excitons, but they do for some reason. So this was a very big puzzle for us. And we came across some papers by a group from Toronto, Sargent, that is one of the leaders in the field, where what they were doing is they were checking also the difference between these two, but looking at the difference between the quantum yield. These apparently have a much higher quantum yield than these. And they were looking at the atomic displacement parameters. Atomic displacement parameters, when you do crystallography of your structure, and these are, you do crystallography on these, atomic displacement parameters, you get them for free in your crystallography data. People normally don't look at them much, but they're basically your error bar on your crystallographic data. Single crystal crystallography, they're your error bar. They're basically, your measurements saying like, well, we more or less know that the atom is there, but you have this uncertainty. And what is interesting about the atomic displacement parameters is that depending on how rigid your crystal is, your atoms are going to be more localized or in place. So your atomic displacement parameter is smaller. So more flexibility in your structure is going to result in a larger error bar on your crystallography data. And you can see this when you compare phenethylammonium and butylammonium, and we're looking at the octahedra unit cell here, but actually you can look at all of them, where you see that butylammonium always has a much larger error bar than phenethylammonium. So now this, our atomic displacement parameter, is now a measure for how floppy my perovskite is. They're very soft semiconductors compared to silicon. Like things can move, they're ionic. Yeah? So apparently phenethylammonium is much more rigid than butylammonium. And you can rationalize that from a chemical perspective. So here actually the ligands are anchors. There's pi-pi interaction. It's not so easy to move this inorganic layer. Whereas here there's no real anchoring going on, and your organic layer can move more freely. Now these are just 2 points on a graph. Now is the diffusivity. So how fast do they move as a function of how soft my material is, my atomic displacement parameter. Where you can see that phenylethylammonium and butylammonium are at 2 extremes. You can do chemical design. You can make a PEA with a fluor here. Then what happens is not something that you really design, but it just happens to crystallize in that way. You get much stronger pi-pi interactions, and your diffusivity is higher. Atomic displacement parameter, smaller, more rigid, higher diffusivity. You can also change the length of your alkyl chain when you make your butylammonium, and you can make the whole family. Where now you make it farther and farther spaced about, everything is even more floppy. You can see that there's a very clear trend of high diffusivity with higher rigidity. This is now what we would like to, call a structure property relationship, where you can say, like, okay, look, the design parameter apparently is rigidity. Okay, good. I'm gonna close, but otherwise it's gonna get very, 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 very long. Just to mention that this point, where we start to be subdiffusive, is something that we can quantify as well, and we can model, and we can analyze. This is basically telling you something about how long it takes me. I also know how fast I'm moving. So what does it take me to reach the traps? What does it take me to reach defects? So the point of inflection here is telling me about the trap density inside my material. Because that's where I start slowing down, when I reach the traps, because then I get trapped for a little bit, I maybe move on, but things start slowing down. That's the trap density. You can analyze that. You can do a lot of things, especially if you work with Rafael Delgado, because he loves these kind of measurements. Good. I'm going to skip now a lot of slides, because we've done a lot more work, but I just don't have the time to tell you about it. So one of the interesting things is that everything that I've been telling you now has been work based on laser diodes. Laser diodes are not, they're very easy, because you just flip of a switch and start measuring. They are limited to 100 picoseconds, which is why all the time scales that I've shown you, are maybe like some bit of sub-nanosecond, and then you measure what is going on. Now we are implementing a pump probe technique that is based not on fluorescence, but on measurements of changes in the refractive index when there's a carrier, which is a story in itself. When you do pump probe, you can switch to femtosecond lasers, and you gain 3 orders of magnitude. So the movies that we are going to make now are going to be 3 orders of magnitude higher temporal resolution as what we've had till now. So we hope to get even more information there. And of course, for that, I thank very much my funding agencies. I want to do one last thing. It is not related to, well, it is actually related. So a few months ago, well, I already mentioned, I'm coordinating this climate course here at the Autónoma. Even though we are doing very fundamental research, I think it's also important to still keep in mind why we are working on energy research and everything. So we started this project, which is in collaboration with the Fundación Española de Ciencia y Tecnología, so the FICIT, basically the Alcobendas Science Museum is also from the FICIT. And we started this project, which we call En Cambio, which has a wordplay in it in Spanish, to start, translating some of the content of this course, which is for university students, to primary school students. So this is a completely different kind of thing, but we are making small videos that teachers can use in the classroom, where we are collaborating with Norarte to make, educational videos on the basic concepts of what is climate change and what is the energy transition, which for me is very motivating to do. And also, just as a general announcement, this is not very periodic. We do it irregularly, depending on when people are available. We are organizing climate colloquia with experts. We are not experts, because I only work in energy transfer on a nanoscale. There's experts on many different topics in climate change. We've already had a colloquium from Jorge Olcina, as well from Stefan Ramstorff. So I would like to also announce these kind of things a little bit to get as many people interested as possible. With that, I would like to thank you very much.
Six.
66. Yes.
You will relate that to the energy disorder.
Yeah.
But obviously, especially in the larger scale of integers, you see that there is disorder in the distances as well.
Yeah.
And of course, it will slow down the diffusion when you have to reach particles which have less neighbors or more distant neighbors. So you must also take into account the distribution of distances.
Yes. Yeah. So this is interesting.
And not only that, this also will be influenced by the distance dependence of the energy transport. There's some old theories in Putti, Hirayama or something, which describes energy, the distance dependence of energy transport due to multiple interactions, for example.
Yeah.
And what is more, you also have an anisotropy because you have these rectangular particles, apparently rectangular particles, which really has to do with this structure.
Yeah.
Which will introduce an anisotropy in the diffusion. And then in an extreme case, it would be one dimension.
Yeah. Yeah. So what we see, to answer your last question first. So what we see is that even though there is some anisotropy in the shape, that anisotropy, if you look at a larger scale, is random. So that should not lead to a very distinct one-dimensional thing. We also measure in different directions and you don't see such things. That is the first thing. The first question: does structural disorder lead to anomalous diffusion? Only in very extreme cases. Why? Well, first of all, if that happens, you get to a subdiffusive regime because the last particle has less neighbors. That last particle that has less neighbors is a smaller particle, not a bigger one. The bigger one always has more neighbors on average. So if the structural disorder is dominating the subdiffusive part, you will see a blue sheet, not a red sheet. So that's important.
That's all the distribution of
Yeah. No, but we have. I don't have them here. We have a whole set of Brownian dynamic simulations with different distributions, where you really have to go first of all to deviate from a straight line. Only taking structural disorder into account, you really need to go to fractal-like distributions. It's very difficult to actually get something that is not normal diffusion if you don't take into account energetic disorder.
Diffusion is something of a very global thing, and it doesn't reveal the details of what is behind.
Of course. But these Brownian dynamic simulations, what they're doing is they're taking the energy transfer, so it's a discretized model where you don't treat it as a diffusion, you treat it as, okay, what is my transfer rate, one particle to the next? And if I make that, the key there is that if there is no energetic disorder, then that individual transfer step, I'm not talking yet about how many neighbors you have, that individual transfer step is equal moving from A to B as from B to A. If I have energetic disorder, then moving from A to B is not the same as moving from B to A, because one is downhill and the other one is uphill. And that effect, to make basically the transfer rates asymmetric, that is what results at the end in your subdiffusive behavior. Whereas the other one, you really need to probe a very large area, and we know that we are not moving very far. We're moving 80 nanometers at best. So actually, you're not making many hops. You have something that lives very, very long, and you can probe your entire structurally disordered thing, then you can start seeing some diffusion. That's on a very different time scale, very different max scale.
When you have different sizes of solution, have you considered that you might also have different efficiency to expressions for the
Yes, yeah. So this is very interesting as well. Of course, how curved your particle is typically induces more defects. So people say like, if you have a larger surface area, then also you have maybe more defects in your particle. What we actually see is that the quantum yield goes up going to smaller particles. So that means that these have less defects than these, which again does not fit with the more subdiffusive behavior that we are observing here. If it would be defects, then these ones again should be the worst because the quantum yield is lower.
At the beginning of the talk, talk a bit about QLED TVs, and you mentioned green and red beacons. What's going on with something related to the high temperature induces some sort of beacons?
Oh, all right. So there's a lot of marketing behind this, right?
Yeah.
So they call it QLED. The Q is the quantum dots, the green and the red, and the LED is just a blue LED. Because it's a backlit. It's a backlit TV. So what the blue LED, that is your back plane of your TV, is doing is it's just exciting optically your red and your green quantum dots. They emit, and then you get your red, green, and blue. There's no LEDs in there that are quantum dot LEDs. This is the first trick. So of course, and then the other problem is that with cadmium selenide, well, you can go to cadmium sulfide, but the problem is that the chemistry is at some point just becomes difficult depending on the material that you're working with. And if you really want to get blue emitters, they need to be so tiny that again you get into the same story as what I've told here. If you go to a very, very quantum confined system, and adding or subtracting a single atom is going to change your bandgap. So it's very difficult to make really tiny particles monodisperse. Then we're going into what they now refer to, and is actually David Norris as well. Yes, probably a series of articles on these, which are calling now the magic-sized nanocrystals. Okay, be able to synthesize that and take that to industrial scale is a whole separate story. The magic-sized nanocrystals is the same thing as what people have been doing with gold nanoparticles in catalysis. That people are talking about clusters more than nanoparticles. It seems that now they are getting the handle on it to be able to do that with cadmium selenide, but to really have every particle being the same number of atoms. But it's very difficult to make a very good blue emitter for that reason, because you need to go to very small particle sizes.
It's interesting to know that no matter if you change technology from banding divided using diodes or on, you always find the problem of blue emitters.
Yes, exactly. Blue emitters are difficult.
Thanks for the talk. In the case of the 2D perovskites, the acetone are moving to the. Then, when you send the separation between the 2D materials at the end, you should obtain just appear 2D materials, and the diffusion are going to zero. That confusion is so.
Yeah. Okay. So I went very fast over those slides. I mean, zero is a big word, because even though that diffusion is quite small, it is still much faster than any of the quantum dot stories that I've shown you. So everything is a matter of scale. Here, it's small, but it's not zero. This is still as fast as some of the quantum dots. All right. The little bit more elaborate story here is that, of course, in perovskites we know that we're not really dealing with just an exciton, but that the presence of the exciton deforms the lattice, so it's actually a polaron. So what you're moving is not the exciton in the lattice, but you're moving a deformation of the lattice, which is why it gets why this is so dramatic. So you slow it really down because the polaron becomes much more dominant here than it is in a rigid.
That is another curiosity, just how the energy of the exciton change as you increase the separation.
A little bit. Okay, so then we go, so I've talked a lot about quantum confinement. So quantum confinement is basically just the size of your semiconductor. But when you make semiconductor very, very small, and this is especially the case for a 2D perovskite like this, you have your exciton here, and it lives in this plane, but its electric field lines are actually outside. So then we have the additional correction on it, that is the dielectric screening, that depending on the dielectric constant of what you have surrounding your particle, you're going to get smaller shifts, but still shifts in the emission spectrum. That you see clearly. So the emission spectrum is slightly different from different organic cations. That's the dielectric confinement.
This effect of the softness of this material can be included in the electric constant, the intermediate region in this scale is formally. So.
Yeah, we have not gotten into that. So one thing that is very difficult with perovskites, there's only a few groups in the world that are able to do it, is basically doing proper DFT. Because they're very heavy atoms and unit cells are typically quite large. So you need to really have the capacity to be able to do good DFT of these kind of things. So there are studies, but it's very specialized work. So we have not gotten that. For us, it's more like at the end it's a little bit hand wavy, phenomenological. See that there's a clear relationship between softness and everything, but to study the polarons, that is a
Connected to that question, I mean, this technique could it be adapted to measure charge transport?
yes.
Like, for instance, doing that reflection,
So it can be done for charge transport when the charges find each other and they're emissive. You can do exactly what I've shown here, using fluorescence.
Yes.
If it is not very high quantum yields, then right now what we are implementing is this measurement that is based on measuring the reflectance. So we are seeing such a pity. I had so many more slides.
But you need
No, you excite, great excitation. What you're doing is you're ever so slightly depleting your ground state. So you're changing the absorptivity of your material. Change the absorptivity, and Kramer-Konitz tells you that you're changing the refractive index of the material. So the presence of a carrier changes the refractive index of your material locally by a tiny bit.
Yeah.
But apparently, and I'm showing you here a movie of bulk tungsten diselenite. This is not emissive, right? This is a multi-layer transition metal dichalcogenide. This is delay before the laser pulse arrives. This is pump probe. Then you see a laser pulse arriving and the carriers inside your bulk tungsten diselenite diffusing outwards, simply because the refractive index is slightly different in the presence of carriers. So yes, you can do it. This is not easy. We are getting there. But
at the end, this is a very fundamental question, because I guess if you want, for instance, we are thinking on LEDs.
Yeah.
You are very concerned about transport, just transport.
Yeah.
Probably you don't want excitons to move too much.
Right. So
and there is an engineering problem there that has to be solved, and requires visualizing this.
This is a very good point, right? So if I'm trying to make an LED, the last thing that I want is that my exciton starts moving around, because the only thing it can do is find the quenching site and die. If I make an LED, then I've taken a lot of effort to create an exciton, and the only thing that I want is that the exciton recombines and emits light, because that's the purpose of an LED. If I'm making a photodetector, or if I'm making a solar cell, then yes, and I want things to move around, because they need to reach the electrodes, which are separating layer, etc. So depending on the type of device that you're making, you might want a lot of diffusion, or you might want things to just stay where they are. Right? But still, in an LED, you need to inject free charges, and you want your exciton to stay where it is.